this lecture, we will continue our review and focus on rational functions, and in particular, Hill functions. And we will extend the same dominating power analysis to actually come up with pretty detailed sketches of both of those types of functions. In general, rational functions are functions of this form. F of x is a polynomial p of x divided by the polynomial q of x, so a ratio of two polynomial functions. Now, of course, we cannot divide by 0, so the denominator here will not be allowed to be 0. Rational functions come with asymptotes, vertical asymptotes, horizontal asymptotes, and slant asymptotes, which we will not really talk about, so I'm not going to really review. Vertical asymptotes are fairly easily calculated if we have a rational functions in simplest terms, which means that the denominator and the numerator do not share factors. Then vertical asymptotes will be produced when the denominator of the function, or the bottom of it, is equal to 0. Horizontal asymptotes are going to have to be calculated slightly differently. So if we think in terms of the vertical asymptotes, they're the things where as the function approaches the asymptote, it goes off to either positive or negative infinity as it approaches an asymptote here. Whereas for horizontal asymptotes, it's not near the asymptote behavior in terms of x. Rather, a horizontal asymptote is a value that the function approaches as the x values become larger and larger in either the positive or the negative directions, which means that for horizontal asymptotes, we're going to look at the end behavior of the function and take the limit of our function as x goes to positive or negative infinity. If this limit comes out to be a number, then the horizontal asymptote exists. If this limit comes out to be infinity, that means that the function itself grows unboundedly and therefore there's no horizontal asymptote. In terms of rational functions, there are of course infinitely many of different types, but we will be interested in particular in so-called Hill functions. And these are rational functions of a very particular kind, the functions that look like this, where a and b are constants and the powers of x are the same on top and the bottom. Hill functions are named after the British physiologist Archibald Hill, who studied them in a variety of applications, and in particular in protein binding and muscle physiology, that he actually received the Nobel Prize in Medicine for in 1922. Because of their applications, we will consider these functions mainly for positive values of x. They will model things like population growth, disease dynamics spread, and once again, enzyme kinetics. So these will be things like the number of infected people, the number of animals or humans in the population, or concentrations, and therefore be positive. Now, we can again, of course, sketch this using technology, but we will use the dominating power analysis to really figure out what these functions look like. Let's take a look at one particular example here. So I have 5x squared over 3 plus x squared. This is what we would call a quadratic Hill function because we notice that x is to the power of 2 in both top and bottom. Now, if I am to sketch this, we will apply the dominating power analysis for small and large values of x, but in order to sketch at least some point on the graph, let's compute the intercepts of this function. So for the x-intercept, I'm going to set y to be 0, which means that what I have is 5x squared over 3 plus x squared has to be 0. And now I'm going to look a little bit closer at this. What this is saying is that I have a fraction equals to 0. Well, the only way a fraction is ever 0 is if the top of it is 0, which will give me 5x squared is equal to 0, which of course will then give me that x is equal to 0. If I were to compute the y-intercept, I'm going to set x to be 0, and then what am I going to get? I'm going to get 5 times 0 squared over 3 plus 0 squared, so 0 divided by 3, or 0. So my only intercept of this function is at the origin, when x is 0 and the y is 0. Good to know. This gives me a point to plot on the graph. Now, I am going to utilize the power analysis, which means I'm going to analyze what my function looks like for small values of x, as well as what it looks like for large values of x. So what am I going to have in each case? I'm going to think about what my function will approximately look like here. I am looking at this Hill function here. It's a rational function, which means it has the numerator and denominator. For small values of x, the power analysis suggests that the small powers will dominate. I will analyze the top and the bottom separately. So let's look at the top here. Well, there's only one power function on top, so I don't have a choice between what dominates what. 5x squared will be there no matter what I pick, whether it's the small values or the large values of x. On the bottom, though, I have a choice between two terms. The power function 3, it is a power function, it's just a bit of a trivial one. It's 3 times x to the power 0, which is just 1. So this is a power function, and x squared is a power function too. So among these two, I have to pick the one that will dominate for my particular case. If I'm looking at the small values of x, I know that the smaller powers dominate, so I have to pick one of these, which is the smallest. Now again, this is like 3x to the power 0, so the power function among these two that has the smaller power is, of course, the 3. So this is what is going to remain for the So let's take a look at what I have here. My function is 5x squared over 3 plus x squared. What's going to happen to the numerator and denominator for small values of x? What are they going to approach? Well, in the numerator, I don't really have a choice. There's only one term there, 5x squared, so I have to keep it. But on the denominator, I have two power functions to pick from, 3 and x squared. For small values of x, the smaller power will dominate. So which term has the smaller power? Is it the term that is a 3, or is it the term that is x squared, which has a smaller power of x? Well, you can say 3 doesn't have a power of x at all, and that's true, except for we can rewrite this as 3x to the power 0, and then it's easier to compare, and it becomes very clear that 3 is the term that has the smaller power of x, which means that it will dominate for smaller values of x. For small values of x, I'm going to only keep the smallest power of x. For large values of x, I'm going to do the analogous analysis, but keep in mind that for large values of x, large powers dominate. Again, on top, I don't have a choice. There's only one term, so I have to keep it. But on the bottom, I have to choose between 3 and x squared, and I have to keep the largest power of x. 3 and x squared. X squared is the term with the largest power of x, so I'm going to ignore the 3 and keep the x squared. Now that means that for small values of x, my function behaves like 5x squared over 3, and for large values of x, my function behaves like 5x squared over x squared. Now I can rewrite both of these in a slightly more visually sort of pleasing or visually suggesting way. So for example, I can rewrite this as 5/3 x squared, and it makes it very clear immediately that this is just a parabola with a positive coefficient, so an upside looking parabola. Whereas this term altogether, I can see that I can actually cancel x squares and overall end up with 5, a constant. Recall that what I am doing here really, when I am analyzing what happens for large values of x, is taking analysis of end behavior of the function, which corresponds to the horizontal asymptotic behavior. Now, with all of this information, I can already sketch the graph of the function. Remember that I'm only interested in doing so for positive values of x, so I'm not even going to bother drawing any other quadrants. So what I have discovered is that my function has to go through the origin, so I can plop the point over here. For small values of x, my function looks like an upside facing parabola. So this right here is 5/3 x squared. And what I know is that for large values of x, my function has to look like 5, which is, of course, a horizontal asymptote of my function. So if my function has to look like something of a parabola here and has to approach the horizontal asymptote of 5 here, I can just connect the two pieces into a shape that looks like this. Now, again, remember that this is a qualitative analysis, which means I'm not actually interested in the scale on other of the axes, well, except for the 5 here. Once we discover other potential quantities or qualities about this function, we might have to put more information on the graph. This is one of the Hill functions, but remember that the actual powers can differ. And in fact, one of the biggest applications of the Hill functions, and in particular linear Hill functions, are in enzyme and substrate reactions. So for a little bit of context, this is how they work. They go through a cycle of several steps. We're going to start off with an active site that is provided by an enzyme. A substrate is going to bind into the active site. The reaction is going to happen, and the substrate will be converted into products. So in this case, separated into two and released separately. Once another active site becomes available, another substrate binds to it, and so on and so forth. We will go through this cycle as many times as the reaction will take place. There are a couple of things to note right away. First of all, if there are many substrates available, so the concentration is very high, the reaction will of course be faster because they will be binding to available active sites as soon as one actually gets freed up. Available sites will not be sitting idle for long. That's on the one hand. On the other hand, though, if the concentration of the substrates is really high, then there are not going to be enough active sites available to continue speeding up the reaction. So with high concentration, the actual reaction time will decrease because the active sites will be constantly occupied and not be able to provide any more of an actual increase in speed. So this is essentially the two basic ideas behind the Michaelis-Menten kinetics that describe the speed of a chemical reaction as depending on the concentration of the substrate. When there's no substrate present at all, the speed, of course, is going to be 0 because nothing will be able to bind to the active site. However, with the high concentration of the substrate, the speed of the reaction will reach some maximal level. It will be quite fast at first and then will plateau out for the high concentration of the substrate. This already describes what we have seen in terms of behavior of the Hill functions, where we have a plateau or a horizontal asymptote that it will approach. And in fact, this is exactly what is described by Michaelis-Menten kinetics. Here is the formula for it. So x is going to be the concentration of the substrate, and what we have here is a linear Hill function with the graph that we're going to produce in a little while, but has the same behavior as the actual Hill functions that we have seen before. A couple of things to note here about the people behind this law. There are two that are named after Michaelis and Menten. Michaelis, Leonor Michaelis, is a German biophysicist, and Menten, or Maud Menten, is actually a Canadian physician. So not only is she Canadian, she has very specific links to British Columbia and actually Fraser Valley in particular. She was born in Ontario, but her family moved fairly quickly after her birth to Harrison Mills in BC, and this is where she actually started her education. She received several degrees from Canada. She actually went to University of Toronto when she was an adult and received a Bachelor of Arts degree and then a master's degree in physiology. But at the time, it was nearly impossible for a woman to receive any higher degrees than that in Canada, so Menten had to travel abroad. She went to US, she went to Germany to work with Michaelis, where they came up with this law, and she came back to US to actually receive her PhD in biochemistry. She has quite a career, and she was known to be quite a character. In particular, she was very fond of arts her entire life, and she was very interested in learning different languages. And in particular, because she went to school in a small town in BC, a lot of her classmates were indigenous to the land, and one of the languages that she spoke fluently was Halkamelim, the language of the Stolo people. I encourage you strongly to look up the biography of both Michaelis and Menton, because the people behind these discoveries are truly interesting characters. Menton is also, another fun fact about her, actually inducted into the Canadian Hall of Fame for medicine. So let's take a look at this function that these two scientists actually studied. And let's see if we can sketch it a little bit more precisely than my very hand-wavy previous sketch. We will analyze it the exact same way as we have before, using the power analysis. So what happens for small values of x and what happens for large values of x. So for small values of x, let's start off with our function and think about the power analysis. On top, as in the previous slides, there is nothing to choose from, so we have to keep the term that is currently there. On the bottom, though, we have two terms, the constant and the linear term. So again, for the constant, you can think of this as b times x to power 0, because this is just 1, but it will at least introduce the power of x so we can compare it to. For small values of x, small powers of x dominate, which means that we will ignore the larger power of x and keep the smaller one, which is just b. And it makes a little bit more sense if we rewrite this as a over b times x, because then it's clear that this is simply a linear behavior where the slope is a over b. What happens for large values of x? So for large values of x, our power analysis indicates that we should be keeping the larger power of the x available. So again, on the top, there's nothing to pick from, so we're stuck with the term we have. And on the bottom, the larger power is going to be x. Here, x's will cancel, so we will end up with just a. And as we have seen before, this will produce the Hill function that has a behavior near the origin that corresponds to small powers of x, or a line with slope a over b. So something that looks like this. And we can even annotate it saying that this has slope a over b. And then it continues on until for the large values of x, it has to behave like just a horizontal line at a. So it's going to reach this asymptote and approach that. So this is, of course, in line with our observations that with no substrate present, the speed of the reaction is in fact 0. But with high, and first, when the concentration goes up, the reaction speed goes up fairly quickly, but at very high concentrations, this is no longer the case. And in particular, we can notice is, let's say I start with a small concentration and I double it, the speed of the reaction will grow quite a bit from this speed to this speed, quite a bit of an increase. But if I start with a high concentration and I double that, if I look at the corresponding speed of the reaction, so the y-coordinates of these 2 points, they're much closer together. The increase in speed here was essentially trivial, right? So for small concentrations, the difference in the reaction time is big. For large concentration, the difference in the actual concentration is fairly small. The general Hill functions are, of course, of different degrees. So we start off with the linear as the Michaelis-Menten kinetics, but we can also think about various chemical reactions taking place that will probably correspond to slightly different behaviors that are also described by Hill functions. So let's take a look at what would these look like if they are all sketched on the same graph. Now, of course, again, the analysis is going to be the same. We have to think about the small values of x, and we have to think about the large values of x. And so for each one of these functions, let's take a look at what the behavior is going to be. So I'm going to make this big table, and I'm essentially going to line it up to the functions that I have up top so that I can fit them in nicely and aligned. Okay, in fact, I actually encourage you to pause the video right here and fill this table out by yourself, because this is simply going to be once again using the power analysis that we have already seen before. Okay, so for small values of x, the small powers dominate, and the small powers on the bottom of all of these functions correspond to the actual constant. So for this function, for small values of x, we're going to have ax over b, ax squared over b, and ax cubed over b. Now, it might be easier if we rewrite these as a coefficient times the x. So instead of saying it's ax over b, it's probably more straightforward for graphing to say that I'm going to separate the coefficient and keep the power of x. Same thing here. It's going to be a over b times x squared. That way, it's a little bit more clear what the actual graph will look like. And so finally, for the last one, I'm going to have a over b times x cubed. Now I see that this is just a line with slope a over b. This is just a parabola that has been stretched or transformed with this factor. Now remember that a and b are both positive constants, so this is still a parabola looking up. And this is a cubic, snaky function that again has been stretched out as according to these constants, but them both being positive means that it's going to be our regular snaky shape. For large values of a, the large powers of all the denominators will once again dominate, and so we're going to end up with ax over x, ax squared over x squared, ax cubed over x cubed. And of course, notice that in each one of these cases, the x's will cancel themselves, leaving a as the AND behavior for all of these cases. Okay, so now let's put all of these three functions on the exact same graph. So once again, because of the actual applications that we're going to be working with in terms of Hill functions, I am only interested in sketching this graph for positive values of x. So I noticed that all of them are going to have a as their horizontal asymptote. So I'm going to have the a as the horizontal line going here. And now let me start drawing from the smallest power of the Hill function to the larger. So this first one, we have to have a near origin behavior as a line of slope a over b. So I'm going to start off with a straight line. And then, of course, I have to once again approach this asymptote. So as in the example before, I'm going to start with the linear function, and then I'm going to carry over in order to approach the asymptote. So this is my linear f of x. That's the name of this one. Now, next up, I have a quadratic. So that means that near the origin, this function has to look like a parabola. But then for large values of x, it has to approach a. So this is where the other part of the power analysis is important to remember. For large values of x, these both approach the same number. But for small values of x, they are linear versus quadratic, which means that in the beginning, the smaller power will dominate, so the linear function will be on top, but later on, the larger power has to switch over and start dominating. The quadratic function will eventually have to beat out the linear function in how fast it grows. So I'm going to have a switch over at some point there. I start off with a parabola, and then at some point, I switch over to dominate the linear function. So this is going to be my quadratic Hill function that's in this case called g of x. And then my last case here is the cubic. So near the origin, it's going to behave like a cubic function, and I have to decide where it fits, right? So once again, the power analysis says that near the origin, the smallest power will dominate, which will be linear, followed by the quadratic. And so the highest power will be the flattest near the origin, but at some point it will have to switch and start growing faster than any of the other two functions. So this is going to be the case with my cubic. I'm going to start at the bottom here, going to switch over, and eventually dominate both. So this pink one is going to be my cubic function that is called h of x here. Okay, this is really a great way to think about how the different Hill functions interact with each other. The near origin behavior is described by the smallest powers in the denominators actually dominating, the end behavior is always approaching a constant, so always this kind of saturation limit in terms of chemical reactions. And the switch point is governed by the same laws as any other switch point for the actual polynomial functions. The smallest power dominates near the origin, and then the largest power dominates for large values of x. Now, these are what we call continuous functions. They are where every single point corresponds to the point on the graph. On the flip side, we might have something that is given by data points that are discrete. So let's take a look at this application of the sockeye salmon population in Skeena River. Skeena River is the river in the north of BC. So we in Abbotsford and Chilliwack, we're just in the general lower mainland, is somewhere around here. This is the Skeena River river delta, and so the salmon is the salmon population in the Skeena River has been tracked really carefully from the early 1900s, and we have a lot of data that's connected to the population numbers of salmon in the Skeena River. So this is something that we can model mathematically. Generally, salmon population is tracked fairly closely in British Columbia because this is one of the sources, of course, one of the biggest industries here, but in particular, it is a very important industry, has always been for the indigenous peoples of British Columbia. Salmon has a really fascinating cycle of life. Not only do they breed in only specific freshwater lakes, their offspring migrate to the ocean to mature, and they return to the exact same lake or riverbed where they were hatched to, in fact, produce the offspring. Once they breed, they die, and they feed their remains feed the actual environment around them. And then once their offspring hatch, the exact same cycle repeats over and over again. Skeena River is home to Tsimshian and Gitxan nations, whose names are beautiful, meaning inside the River of the Mist and people of the River of the Mist. Because Skeena salmon is of the high importance to indigenous people, and because the area has been mostly unaffected by the industrial human development in the early 1900s, we have very good data on the salmon population and how it actually reproduces and what that means for salmon numbers without a lot of industrial human intervention. These are the numbers of salmon in thousands as they have been tracked through the early 1900s in the salmon river, in the Skeena River. So what we would like to do as mathematicians, of course, is to be able to predict these numbers into the future. So for example, if you tell me the size of the population in 1 year based on the previous data and my previous knowledge and general knowledge of how salmon reproduces, how can I predict the number of salmon the following year? So what I did was simply take these numbers and come up with a mathematical model. Now, because the data here is what we call discrete, which means given at only specific point and not at every single year throughout, you can think of this as the analog of, let's say, Newton's method, where the entire process is iterative, right? So if I have x naught as my initial population, the following year I'm going to have x1, the year after I'm going to have x2, x3, and so on. Now you can see here that my intervals are always at 4 years, so I can keep the indices here sequential as well. So I just put together these numbers and I came up with the following formula, that x sub n plus 1, so the n plus first iteration, so the n plus first steps from my initial population of 1098 in year 1908, the formula looks like this. I have 8.9637 xn all over 1 plus 0.0111899 xn. Now, real data produces sometimes really quite complicated looking things. But if you just squint at it a little bit and recognize that these are just pretty big constants, you will see that the general structure is familiar. This is simply a hill function, a discrete analog of a hill function. I have some kind of a number here, a constant, times x, 1 plus some kind of constant here times the x. Not only is this a hill function, this is a linear hill function, so I know fairly well how it's going to behave. Now, just to get the hang of these computations with the indices and to remind ourselves sort of how this works out, what I would encourage you to do is to try to calculate, given this formula, try to figure out what is x1, given that x0 is the number in 1908, so 1098. And then again, just to get the hang of using this big ugly looking formula, try to calculate x2, given that x1 is 740. Remember that this is the formula that I came up with for this data, but I've actually only used up the first 2 years. So the further we go into the future, the more inaccurate my model will become and will have to be adjusted. But because this is a discrete analog of a hill function, we can actually generalize this and we can sketch this fairly well. Now, I could have used any other function to model this with, but I chose the linear hill function specifically because this is closely related, or rather, this is exactly one of the most accurate and precise formulas for the description of the fish population growth, known as the Beaverton-Holt model. Now, in general, the model relates the population this year, x1, to the population of last year, x0, but it actually works best for fish populations. This is the general formula. Again, just a standard hill function of degree 1. And so the only other thing that is different from this than the general hill function is the fact that the coefficients look slightly different. So the a and b here are not quite in the same place, and we insist on this being 1 in the most standard Beaverton-Holt model description. Okay, so just because of this slight difference, let's go through the analysis and sketch this x1 as a function of x0 to see if it has a very clear connection to the Michaelis-Menten kinetics and the linear hill functions. Okay, so just like we did before, near the origin and end behavior, let's go through this and see if we're going to see something similar as we expect to see. So what do I have here for x1? Let me rewrite this, ax0 over 1 plus bx0. So what am I going to see near the origin? Near the origin is where I care about the small values of x, which means this is where I care for smaller powers of x. On top, I have no choice. I have to keep the only term there is. And on the bottom, remember that my variable is x0. Between these two terms, I am looking for the term with the smaller power of x, which is the constant term. So I'm going to keep the 1 here. So rewriting this slightly, I have ax0. So what I have is a line of slope a. For the end behavior, I'm going to see that I have once again the exact same function. I'm going to keep the top because there is no terms to choose from. But on the bottom, for the end behavior, for large values of x, I have to keep the larger power of x, which is bx0. So bx0 here, I can see that my x0's cancel and I have a over b. So my horizontal asymptote here is not the coefficient on top, but rather the ratio of the coefficients a over b. So when I'm sketching my function, I just have to be careful as to how I label the slope near the origin and the eventual horizontal asymptote. So my horizontal asymptote has to be a over b. And near the origin, my function is a line of slope a. So it still is a linear hill function, but the coefficients did affect just slightly what the actual constants mean. The shape will be the same as the shape of the general hill function, except for, once again, the constants will be slightly different. Now notice that I am slightly lying with this graph, and that is because my graph shouldn't be a continuous smooth function. I am given numbers of population 1 year, next year, the year after, and so on. So I actually don't have a continuous smooth curve. What I have really is a bunch of points that will lie 4 years apart. In our case, like for example, in the Skeena Salmon River example, but they will really not be connected to each other because we don't have data points for everything in the middle. Now let's think a little bit more about what these A and B mean in terms of our graph. Notice that the larger value of A, the steeper the initial slope will be, and if A is bigger, that means that this horizontal asymptote will be higher. So larger values of A mean the steeper original slope and the higher plateau level for my function. If I fix the A and I increase the value of B, this does not at all affect near the origin behavior, but this will affect the horizontal asymptote. For fixed A, if B is higher, that means I'll be dividing by a larger number, which means that the overall fraction will be lower. So higher value of B means lower plateau level for the population. Now, what other kinds of questions can we ask in this setup? Let's take a look at this here. Is there a population level X naught that would be exactly the same 1 year to the next? Which means that is there a population at which the process will stabilize? This year's population will be exactly the same as next year's population. And we're asked to compute this for the Skeena sockeye salmon as well. Let's compute this in general and then plug in our particular data. Let's take a look at our model here and really think about what it represents. So X naught is the population last year. So the model says that given the population last year, if I plug this into this formula, it will predict the population for this year. What our current question is asking is when the two of them will be the same. So the population from next year, which our model predicts to be this, has to equal to the population from this year, which is actually X naught. Okay, so take a look at this again as compared to the formula with the actual population growth. I would like next year's population, X1, to be exactly the same as this year's population, X naught. Once I have this equation, I simply have to solve for X naught in terms of A and B because those are just constants. So what I can do here, well, first of all, I can just cross multiply to get rid of denominators. So what am I going to get? I'm going to get that X naught times 1 plus BX naught is equal to AX naught. I can move this term to the left and factor X naught out. So I'm going to have, let me do this in 2 steps. I've moved this over to the left, and then I noticed that this big term has X naught, and this term has X naught as well. So I can take it out of the entire brackets. And in the brackets, I'm going to have 1 plus BX naught from this term here. And once this X naught traveled outside, I'm going to have minus A is equal to 0. And once again, factoring is fantastic because either that means that X naught is equal to 0, or it means that this entire bracket is equal to 0. So X naught equals to 0 means that this year I have no population. Well, if there's no salmon this year, there's not going to be salmon next year. So this is one of what we call stable points or equilibria. What about this equation? Can I solve it for X naught? Well, let's see. If I move 1 and minus A over to the right, I get A minus 1, and then I can divide by B to get the solution to this. There are a couple of things I have to be mindful of here. First of all, if I have a ratio like this, I need to ensure that B cannot be 0, because otherwise I won't be able to compute with it. But also, keeping in mind that X naught is the size of the population, it means that this number has to be positive. So far, my only restrictions have been on A and B being positive, but notice that here I also have to insist that A is actually bigger than 1, so that when I subtract 1, I still end up with a positive number. So my A has to be bigger than 1. And then I have these two possible population sizes that are going to produce the population that's exactly the same 1 year to the next. What do we compute for Skeena salmon? Well, there I can simply plug in the numbers that I have for A and B. So I'm going to have A minus 1 divided by B. My value for A was 8.9637, and then I have to subtract the 1, divided by B, which was 0.0111899. So if I compute this all together, it turns out to be 711 thousandths of salmon. So what this means is that for Skeena River salmon, if the process continues the way that it has and nothing changes environmentally drastically, that if I have 711,000 salmon 1 year, then that's exactly the same number as I'm going to have the next year, and exactly the same number as I'm going to have the year after. Now, of course, in nature, nothing ever is that stable, so we notice that even when the numbers were near 711, they did not produce the exact same number the year after, because again, nature is a little bit more complex than any mathematical model can describe it as, and this is why studying nature is particularly exciting.